For the Thank you so much for the introduction and this and the invitation to speak here. I'm going to be talking about knot physics, which is a geometric unification theory. And what we mean by geometric is we're going to try and explain as much as we can using just the space-time manifold. So we're going to try and explain quite a lot of physics from a geometric perspective. Um, so we know that general relativity is fairly successful at using geometry, the geometry of space-time, to explain gravity. And in that picture, the curvature of space-time is a response to the presence of mass and energy. What else could we potentially describe using just space-time geometry? Of course, the general relativity model is particularly beautiful, in large part because of the simplicity of its assumptions. Can we do more with those same assumptions? Well, physics has particles, and those particles are pretty important to how physics works, but particles are discrete. You can have one electron or two electrons, but you can't have half an electron. And this is in contrast to the nature of geometry, which is generally kind of a continuum. But a topological defect, a knot in a manifold, is a discrete quantity. And so it may be that a knot would be a natural fit for describing a particle in a geometric way. If we move on to quantum mechanics, this is yet another challenge because quantum mechanics allows quantum superposition, where one particle appears to be in multiple places at the same time. But here again, we find that there is a natural geometric object that is a good fit for superposition. And there's a notion of a branched manifold from mathematics, and a branched manifold is in some sense a superposition of geometries. And we can use that notion of a superposition of geometries through this branched manifold concept to explain a lot of what we see in quantum mechanics. And then after we have those two things, the assumptions that we already needed in order to get particles and quantum do a lot of the heavy lifting for us in terms of explaining fields and forces. So that's a little bit of a preview, and let's start to get into exactly how this works. We're going to begin by making a certain set of assumptions, and then from those assumptions, attempting to derive useful and familiar conclusions. So we want to talk about particles as knots, but a knot in an n-dimensional manifold requires that that n-dimensional manifold is inside of an n plus two-dimensional space. So for example, a piece of string is loosely analogous to a one-dimensional manifold. And if I have a piece of string in front of me in this room is a three-dimensional space. And so I can tie that one-dimensional manifold into into a knot in this three-dimensional space. And so this n plus two relationship is how we get knots in a manifold. And so if we want to tie space-time into a knot, then we need to have space-time inside of something that's larger by two dimensions. And so the illustration on the right is intended to convey that, where the blue blue manifold is space-time, and space-time is inside of this larger space, which is loosely conveyed with this box. Of course, the dimensions are not correct here, but the intuition is that we have a space-time manifold represented by this blue manifold, and it's inside of this larger space. So to tie these knots, we need space-time to be inside of something that's larger by two dimensions. So three spatial dimensions in one time dimension, we're going to put that inside of something that has five spatial dimensions in one time dimension. Well, quantum mechanics requires a superposition of states. An electron can appear to be in the left side of a box and the right side of a box simultaneously. And in order to get a superposition of geometries, we use a branched manifold. And the animation on the right is showing a collection of branches that are constantly splitting and recombining. And this will be loosely, intuitively, this animation conveys what we have in mind for the branches of the spacetime manifold, that these branches are constantly splitting and recombining. But we need to prevent that branching from becoming a pathological behavior. In particular, what prevents the spacetime manifold from branching infinitely? Well, to manage that, we're going to introduce a new quantity, and we'll call it the branch weight using the symbol W. We'll say this branch weight is a conserved quantity so that when branches split and recombine, the total branch weight is additive. And so the animation on the right shows a branch of weight 2.1, another branch of weight 3.1, and when they recombine, those weights are additive to a weight of 5.2. The notion here is that if we had, for example, a branch of weight 100, and we introduce this constraint that the branch weight is additive and the branch weight must be greater than or equal to 1 everywhere, then a branch of weight 100 cannot split more than 100 times while keeping that branch weight greater than or equal to 1. So these combined notions that there is a conserved branch weight and that branch weight must be greater than or equal to 1 keeps the branching finite. We're also going to assume that the branch weight is related to the volume of the spacetime manifold. And we're gonna, for this intuitive description, before we get to the mathematics, we're going to describe the volume of the manifold using the word stretching. And so on the animation on the right, we show a sort of a toy model where we have a one-dimensional manifold and we put handles on the end of it. And we imagine using those handles to stretch out this one-dimensional manifold. As the volume of the one manifold increases, as its length increases, the total branch weight has to remain the same, which means the branch weight at any point must go down. And because the branch weight must always be greater than or equal to 1, that means that this one manifold, we can only pull those handles so far away from each other before we hit that limit. And so here we go from a branch weight of slightly over 3 down to a limit of 1. And when we get to that limit of 1, we can't pull that manifold any further. But the branch weight W is now related to two things. It's related to branching and it's related to stretching. And that means that it is the intermediate variable causing branching and stretching to be related to each other. And so if we have this branch one manifold with these handles on the end of it and we stretch it out, the branch weight W again decreases until it goes down to a value of 1. But as that branch weight decreases, the number of branches must also decrease. We can't have a large number of branches when this manifold is fully extended because there's not enough branch weight to support all those branches that are in parallel to each other. The toy model was fairly easy to visualize. It's just a one manifold with these little handles on the end of it. But in higher dimensions, we have another notion of volume, which is curvature. And so if we increase the curvature of our manifold, this familiar blue manifold that we were portraying previously, if we increase its curvature, then as we increase the curvature, the volume of the manifold increases. And if we want the branch weight to sort of see that curvature, we need our branch weight to be able to see that curvature in order for it to take that curvature into account and account for the increase in volume that results from that curvature. And to allow our branch weight to see that curvature, we introduce a new assumption, and we have a metric. We're going to call it H. And this metric H is Ricci flat everywhere. The Ricci curvature of H is 0 everywhere. And then we use H to define our branch weight W in a slightly more mathematical way, where we say that W is equal to the volume element of that metric H. If we do that, then we have this relationship, this desirable relationship between the volume of the spacetime manifold that results from its curvature and the branch weight, such that the total branch weight on this manifold will be conserved even when it's stretching. So this is a little unusual. We have three metrics. First of all, we're inside of a 5+1 dimensional space. We have 5 spatial dimensions, 1 time dimension. And that space that we're inside of has a Minkowski metric. And a Minkowski metric is just, it is the usual metric of special relativity. And it says, it basically is the reason that time is different from space in special relativity. So here we have this bigger space that we're inside of, and that space has a particular metric. That metric is called a Minkowski metric. But then we have space-time that's embedded inside of this. And so because space-time is embedded in a larger space, and that larger space has a metric, this induces a metric on the space-time manifold. And this works the same way as if I have a globe in front of me. I can think of that globe as, the surface of the globe as like a 2-dimensional manifold. I'm sitting in a 3-dimensional room. I can measure distances on the surface of that globe using the same metric as I use to measure distances in the room. And so I can say that the metric of the room that I'm sitting in induces a metric on the globe. Despite the fact that the globe is 2-dimensional, the room is 3-dimensional, by being embedded in this larger space, there's an induced metric on this 2-dimensional manifold. And by being embedded in this larger space, space-time, by being in this bigger space, has a metric that is induced on it. And so we can say that's the second metric. And then there is yet this third metric, H. And the purpose of H is to keep track of the branch weight. And H doesn't really have an analog in the standard model. Really, in the standard model, the only metric here that is familiar is number 2, which is analogous to the metric of general relativity. It is the way of measuring distances on this space-time manifold. So that second metric, the induced metric on spacetime, is the metric of general relativity, and the third one is H is a new quantity that we use here in physics to keep track of the branch weight. So this is the entirety of the assumptions of the theory, that we have this larger space, we're going to call it omega, and it has 5 spatial dimensions and 1 time dimension. We have a space-time manifold M, which is embedded inside omega. It has 3 spatial dimensions and 1 time dimension. We have this metric H, and H, this metric is Ricci flat. The Ricci curvature of H is 0. There's a branch weight that is defined using H as the volume element of that metric, and the branch weight must be greater than or equal to 1 everywhere. And then that branch weight W is conserved when the branches split and recombine. So we can kind of think of these assumptions. The story here is we're going to pull a rabbit out of a hat. And these assumptions are the hat. And the claim is there's a rabbit in this hat. And in this case, the rabbit is all of physics. In order to tell an interesting story about physics, we're going to need some particles, especially fermions. So fermions are electrons, muons, tau, neutrinos. And fermions appear in this theory because we have constraints on this manifold. In particular, we have the constraint that we have this metric h mu nu, which is Ricci flat. And that is a pretty strong constraint on a metric. But there are still degrees of freedom. And even subject to the constraint that we have this Ricci flat metric on this manifold, it turns out that we can produce pairs of topological defects where those defects have homeomorphism class R3 connected sum S1 cross P2. In this talk, we're not going to get into too many of the details about what that particular topology is, but we can say that if it were just R3, that would be flat spacetime. It's just a flat three-dimensional space. And then if we have one defect in spacetime, then that would be the connected sum, R3 connected sum S1 cross P2. And then in the animation on the right, what we're showing is a pair of those defects. So each of those defects is a connection of S1 cross P2 with R3. And underneath, on the lower portion of the animation on the right, what we're showing is that this is loosely analogous to taking a ribbon, an untwisted piece of ribbon, and putting a twist in it, such that we have these sort of two half twists that move away from each other. And the analogy here is a little bit loose. The way that we produce these topological defects is similar to this notion of twisting the manifold, but there is also a fair amount of additional complexity. The idea being that we start with something that is topologically trivial, and even subject to our constraint, this metric H is Ricci flat everywhere, we can still produce these pairs of topological defects. These topological defects are the fermions of this theory, so an electron, a muon, quarks, all of these things are topological defects in the spacetime manifold. The defects, this particular kind of defect that we can make, and this defect is very special, that we have this metric H mu nu that must be Ricci flat everywhere. And the reason that this is the defect that we're interested in is because this is the kind of defect that we can produce subject to the constraint that our metric, that we use H to keep track of the branch weight, this metric H that we're using to keep track of the branch weight, subject to the constraint that H is Ricci flat, we can make this particular kind of defect. But these defects have different embeddings in the same way that if I have a looped piece of string in front of me, that looped piece of string can be the unknot. It can be sort of a trivial loop. It can be a trefoil knot. It can be a square knot. There's multiple ways of embedding a looped piece of string into three dimensions. And there's multiple ways of embedding these topological defects into this higher dimensional space. And each of those different embeddings, the different generations of fermions correspond to the different embeddings of these defects. We remember that we have a branched spacetime manifold, and on the branches of spacetime, if we have one real fermion, for example, one real electron, that one electron will have one instance on each branch of the spacetime manifold. So here we show a branch spacetime manifold with one knot, perhaps an electron, a muon, whatever it might be. And on each of those branches, that knot has a particular position and momentum on each of those branches. And this notion of superposition brings us to quantum mechanics, where the branch spacetime manifold consists of these many branches, and each of the branches of spacetime is a state. If we have multiple branches, we have multiple states. We have a superposition of states. And so this one instance of a particle, or this one particle has multiple instances. Each instance has its own position, momentum, geometry, its own characteristics. And in that way, we have a superposition of multiple states that are all sort of concurrent with each other. These knots can rotate and change size. We remember that we have this spacetime manifold inside of a space that's larger by 2 dimensions. And these knots can rotate and expand in those dimensions. The animation on the right shows a rotation of the knot as if it's rotating parallel to flat spacetime. That animation kind of makes a concession to, we don't have enough dimensions to portray exactly what we want to show. But we have a 3-dimensional spacetime manifold that's inside of a 5-dimensional space, and these knots in spacetime rotate such that their rotation is perpendicular to flat spacetime. It's a hard thing to portray in this animation, but we show rotation in this animation, and then we remember that this rotation is actually happening perpendicular to flat space. We can describe that rotation and using an angle theta. We can describe the size of the knot, the amount by which it displaces into the codimension, the magnitude r. And then we can combine those two into a single complex number k equal to r e to the I theta. And that complex number will refer to the k as the knot amplitude. It describes the size and rotation of this knot. But the knot amplitude is not quite the number that we want. And so we go on to define a quantum amplitude for this knot, which is the product of the knot amplitude, k, and the branch weight, w. And wk, we'll call that the quantum amplitude, and that is the number that we really want. Because quantum amplitudes, it turns out they are additive when these branches recombine. So if I have, in this animation, we show a top branch with a knot, a bottom branch with its own knot, and when the branches recombine, those knots must recombine to a single unique geometry. But that unique geometry that they recombine to has a new knot amplitude, and that knot amplitude is the weighted average of the recombining knots. And so if the top branch has a branch weight of W1, the bottom branch has a branch weight of W2, the top knot has an knot amplitude of K1, and the bottom knot has a knot amplitude of K2, then when they recombine, they'll recombine to a weighted average W1 K1 plus W2 K2 divided by W1 plus W2. And that is the knot amplitude, K3, of the recombined knot. But we remember that the branch weight is conserved, and so the combined branch weight is W3, which is equal to W1 plus W2, and this implies that the new quantum amplitude, W3 K3, is equal to W1 K1 plus W2 K2. The fact that branch recombination causes these quantum amplitudes to add is extraordinarily convenient, because quantum mechanics is a linear theory. And in quantum interference, quantum amplitudes are additive. And here, in this description, branch recombination causes quantum amplitudes to be additive. And so in this description, the claim is that branch recombination is quantum interference. By taking these two branches with a knot on the top and a knot on the bottom, recombining them to get a new quantum amplitude that is the sum of the recombining quantum amplitudes, we produce a geometric model for quantum interference. And we remember that space-time consists of a large but finite number of these branches. And so if we want to describe the behavior on all of the branches collectively, we can take a sum over all of the branches of the quantum amplitudes on each of the branches. On each branch, on branch I, index I, we have a quantum amplitude Wi Ki. And then summing over all of the branches, we get a complex function psi, which is the sum of Wi Ki. The illustration on the right shows this sum where all the branches collectively contribute to this complex function psi. And then if we select a few of the branches out of that set, then each of those branches has its own knot on it, and each knot makes its own contribution to psi, each one contributing its own quantum amplitude to that total. The sum of these quantum amplitudes, sum of Wi Ki over all these many branches, is the quantum wave function. And we could try to describe this discrete system using this discrete sum. But we probably would not have enough information to do that. All of these branches each of them has its own knot. These knots are wandering around, diffusing randomly. Branches are recombining. The knot amplitudes are additive when those branches recombine. It would be very difficult to get the kind of information necessary to describe the state of these many branches at any given time. In the same way that it would be difficult to get full information about all the molecules of water in a glass of water. But what we can do with a glass of water is take the continuous limit and just treat the water as a fluid and model that fluid using continuous differential equations. Similarly, we could take these mini discrete branches and take the continuous limit. It's an approximation that describes this discrete set of branches as a continuum of possible branches. And so integrating over all possible branches and all the paths and all the random walks that these knots take on these mini branches takes this discrete sum to a continuous version of that discrete sum. And that continuous version is a path integral. And in that model, each branch of this branch spacetime manifold is a sum over histories in the sum over histories description of quantum mechanics. It turns out that we don't need to assume the Born rule in this theory. The Born rule states that the probability of an event is in proportion to the magnitude of the square of the quantum amplitude. Well, we have a quantum amplitude, WK, that's defined geometrically. And looking at the geometry, it turns out there's more ways to make a big knot than there are ways to make a small knot. Ways to do something is in proportion to the probability of that event happening. And what that means is that events that involve big knots are more likely. So we can take our quantum amplitude that describes this knot geometry and derive from it the probability of an event that is based on that quantum amplitude. And it turns out that the probability of an event is proportional to the magnitude of the square of that quantum amplitude. And in that way, the Born rule follows from the geometry of these knots. We have enough structure here to describe quantum entanglement without getting too complicated with Hilbert spaces. We can take an intuitive first pass at this by remembering that we have a branch spacetime manifold. And it turns out those branches have structure to them that selects combinations of states. And so if I have a particle on the left and a particle on the right, each of those particles has one knot on every branch of spacetime. And we can associate some sort of quantum information to those knots. For example, in this diagram, we use arrows. That arrow could, for example, represent spin, that we have not yet described what spin is. We'll just say that the arrows represent some form of quantum information. And these branches select combinations of states because on each branch, there's a knot on the left and a knot on the right corresponding to the particle on the left and the particle on the right. And in this diagram, the branches happen to select combinations such that the quantum information, the arrow on the left, is always opposite to the arrow on the right. And that way we have a correlation between these states. Those correlations are encoded in the structure of the branches of this branch spacetime manifold. So now we get to the information part of the story. We have a branch spacetime manifold. It has some knots on it. This sort of sets up what it is the information pertains to. And now we're going to ask, how does this thing behave? And we're jumping into behavior here without introducing any sort of dynamical equations. So we've set up a story that is under-constrained. We have these branches that are constantly splitting and recombining with each other. And we also have the ability to produce these pairs of topological defects, which if they're happening, if that production of a pair of topological defects happens on one branch but not other branches, that implies that they're effectively virtual particle pairs. So we have these degrees of freedom, and subject to those constraints and those degrees of freedom, the spacetime manifold is going to maximize entropy. One thing that we note is that we actually get more distinct combinations of states and in that way more states. When these branches intersect with each other, if I have two branches that are everywhere parallel, if they never intersect, then I have two different states. There's like it can either be top branch or bottom branch, for example. If they recombine in the middle such that you can go from the top branch to the bottom branch, then I have more combinations of states. I have top bottom, top top, bottom top, bottom bottom. So these multiple combinations of states that result just from branch intersection, but more branch intersections there therefore implies more states, more branches. More states implies more entropy. And so there is an entropic pressure for these branches to frequently recombine with each other so that we have more states, more entropy. But if the branches are entropically incentivized to recombine frequently, well, they can recombine more frequently if they're similar to each other. And that means that entropy maximization implies that these branches will tend to stay similar to each other. The animation on the right shows an example where there's a branch on the bottom that is not similar to the other branches. Because it is not similar, it cannot frequently recombine with them. And if it cannot frequently recombine with them, then it's not contributing to those new branches and new states that result from recombination. And so there's an entropic pressure for branches to not do that. They want to stay similar so they can frequently recombine, but reversing the argument, we have this entropic pressure that says these branches will stay similar to each other, and we'll call that tendency to stay similar to each other, that entropic tendency to stay similar to each other, we'll call that branch cohesion. Branches will tend to stay similar. But if branches stay similar to each other, then you can't have a quantum superposition with quantum states that are significantly different from each other. An example of quantum states that are significantly different from each other might be a closed box that contains a cat that is both alive and dead, to use Schrodinger's rather morbid example. Those states would be very different, though they would not be able to frequently recombine with each other. Because they cannot frequently recombine, there's an entropic pressure pushing against that possibility. And so rather than have a quantum system that's evolving towards a superposition of very different states, what will happen instead is that the system will spontaneously collapse to one state or the other. And this is wave function collapse in this theory. We would also like to use this entropy maximization for a broader purpose, which is to describe dynamics. And to do that, we're going to make it a bit more mathematical. We're going to introduce a new function L. We're going to say that L is a pointwise estimator for entropy impairment. We're going to sort of begin from this notion that the spacetime manifold, sort of a nice flat empty region of spacetime, has some amount of entropy that's associated with its branch recombination. If we introduce knots, if we introduce particles, then those particles are going to reduce that entropy of branch recombination. If we introduce curvature, that curvature will reduce that amount of entropy. And we want to know how much is that entropy reduced. And so we're just going to introduce this placeholder function L that's the pointwise estimator. So if I pick some point in front of me and I ask, given the knots and curvature at this point in spacetime, how much is the entropy of spacetime reduced as a consequence of those knots and curvature? L is that amount. And then if I want to know how much the entropy is reduced in some region A, then I just integrate my pointwise estimator over that region. I pick some region of spacetime and I want to know how much do knots and curvature reduce entropy in that region. I just integrate my pointwise estimator over that region. But spacetime is maximizing entropy, and So we're going to be making only small variations around this equilibrium state, around this entropically maximal equilibrium. And those small variations around that equilibrium, the fact that we're staying close to that maximally entropic state means that that value S in some region is going to stay very close to its maximum value. Uh, and And so if we're solving for the dynamics, what we're really doing is we're asking, what can spacetime do that keeps S close to its maximum value? Which means that S that we're using as a measure of entropy impairment is actually also an action in an action principle description of this branch spacetime manifold. And L is the corresponding Lagrangian density. And now we're going to use this tool um, to understand our dynamics. And we want to point out that when we talk about entropy here, this is entropy in a mathematical sense. It is very similar to the thermodynamic notion of entropy, but it is not the same because this is an integral over space and time, in which we're looking at the many configurations of these branches of space-time over some region of space and time. And that is different from sort of the entropy associated with a box of gas, where you look at this box of gas at some particular instant in time. Both of them are derived from a mathematical notion of entropy, but they will wind up having different units because the integral is over a different type of region. It turns out the easiest dynamics to derive from this is gravity, certainly the most intuitive in this picture. We remember that we have a branch spacetime manifold with a conserved branch weight. And so if we return to our one-dimensional branched toy model, as we pull these handles away from each other, the branch weight goes down. And as the branch weight goes down, the number of branches that are possible also goes down. As the number of branches goes down, the amount of branch recombination goes down, which reduces the entropy in branch recombination. And so we see that stretching this thing out reduces the entropy. For that reason, entropy maximization is going to pull back against that stretching. In higher dimensions, when we stretch space-time, we're interested in curvature. And so if we have this embedded space-time manifold and we increase its curvature, increasing that curvature increases the volume because the branch weight is conserved, the branch weight must go down, but reducing the total branch weight means that we have fewer branches for recombination, which means that we've reduced the entropy of branch recombination. And so I'm going to ask, well, how much is the entropy affected? Well, we have a scalar curvature R. That scalar curvature is the leading order approximation of the amount by which the volume changes in response to a change in the metric. And so if we ask how much does the volume increase, the answer is in proportion to the scalar curvature R. If we have just let's say that the branched manifold on the right represents 10 branches that are all very close to each other. As we pull it out, they stretch. Then there'll be a certain amount by which those 10 branches pull back against that stretching. But if there were 1 million branches, then of course they would pull back more. Each of those branches makes its own contribution to the total entropy. And so while the entropy reduction is in proportion to the scalar curvature R, it is also in proportion to the number of branches, and our proxy for the number of branches that are pulling back against that curvature, we're going to use the branch weight W. So W is the total branch weight on all these branches is an approximation of how many branches there are. And so the amount by which the entropy is impaired by this curvature is W, the branch weight, times the scalar curvature R. If we want to ask how much is, that's our pointwise estimator. And then if we want to ask how much the entropy is impaired in some region A, Then it's just the integral of W times the scalar curvature R. We have this branch spacetime manifold, and all these branches, if we have one real particle, that one real particle will have one knot on every branch. It turns out those knots also do affect the entropy. And for the moment, we're going to take all of everything that matter and energy does to affect the entropy of spacetime. We're going to push all of that into a new term, L sub m, whose only purpose is to keep track of whatever these knots and particles do to affect the entropy. We're just going to say it's included within the term L sub m. And then we say that the amount by which, and then to get a sense of how much an individual branch is affected, we say that L sub m has some entropy impairment on a single branch where that branch has weight 1. And then the total entropy impairment over all of these branches is going to be W, the total branch weight in all the branches, W, times L sub m. And then if we're going to ask about the entropy impairment in some region A, again, we integrate over that region of the quantity W times L sub m. But now we have both curvature and matter affecting entropy. And the combined effect is the integral of W times L sub m plus WR. We can use the distributive property of multiplication to pull out W from that product. And then it's W times the quantity L sub m plus R. And then we note that entropy maximization also has an effect on the distribution of branch weight. So if I pick a point in front, suppose hypothetically that right in front of me, there was a point with a total branch weight of 1 million. There's 1 million branches that are splitting and recombining. And then very close to that, there's another point where the total number of branches is 10 branches that are splitting and recombining. Well, that very large difference in branch weight is entropically unlikely, and this branch weight will diffuse so that it becomes closer to a uniform value. So very quickly, I go from 1 million at one point and 10 at another point to 500,005 at both points. So over these short distances, this diffusion is very fast, and the branch weight W will diffuse to being a very good approximation of a constant value. And if W is constant, then we can modify this action principle. We have W times L sub m, the quantity L sub m plus R. But if W is constant, then the extrema of that action don't actually depend on that constant W. So we can pull W out of the equation. And now we have that our dynamics will correspond to the extrema of the action L sub m plus R. But L sub m plus R is the Einstein-Hilbert action of general relativity. And so we see that entropy maximization here on this branch manifold produces dynamics that look very much like the formulation of gravity that is given by general relativity over short distances. However, over large distances, diffusion is a relatively slow process. And so if I look at a point in front of me, there might be 1 million branches that are splitting and recombining. But if I pick some other point in the Andromeda galaxy, it might be 1.1 million. And it might take a relatively long time for that branch weight to diffuse so that those values become equal, become approximately the same. Because this branch weight W may be variable, may change over these large distances, this action W times L sub m plus R will not necessarily be a perfect approximation of the Einstein-Hilbert action over these large distances. And if W is variable over these large distances, then there is curvature the extrema of this equation has curvature that results from that variation. And that curvature does not have a particle source. There is no knot. There is no field that has energy explaining that. It's just variation of W. We have curvature without a particle source that applies over large distances. And this may be an explanation for effects that are currently attributed to dark matter. So over short distances in this description, general relativity is a very, very close approximation of the dynamics that we expect to see. And over large distances, we're going to see curvature that has no particle source that may explain dark matter. The Schwarzschild geometry is a very important geometry in general relativity. And so we want to know, literally, can this geometry fit inside of this higher dimensional space? So remember that we're embedded in a higher dimensional space. It's larger by 2 dimensions. Can we fit a Schwarzschild geometry into that, into a space of those dimensions? And the answer is yes. There is literature that describes this. And so on this animation on the right, we kind of see what it might look like to have a view of gravity sort of from the outside. In the animation, we have a massive object that's at the center. And because of our L sub m plus r dynamics, we have curvature that results from that massive object. The massive object consists of a lot of fermions. Those all contribute to L sub m. And so there's a corresponding scalar curvature r that results from that. And the way that this works as an embedding is that we have these standing waves that rotate inside of this higher dimensional space. And if we pick one particular aspect of the metric to look at, we can examine the time component. And so if we have a clock that is sitting on top of the massive object, that clock also consists of fermions, of course. Those fermions are knots in the spacetime manifold. And so when this spacetime manifold is rotating in this bigger space, those knots, that clock moves along with spacetime. And these waves are rotating in a Minkowski space. So they have velocity in a Minkowski space, and that velocity implies a time dilation. And so that clock on that massive object experiences a time dilation as a consequence of this motion in the Minkowski space. So a clock that's close to that massive object will advance in time more slowly than another clock that is further away, where the amplitude of those waves is smaller and its motion in the Minkowski space has lower velocity. A black hole is space-time geometry at its limit. We remember that matter impairs the entropy of space-time, and so to maximize entropy, we're trying to minimize that entropy impairment. And when we're talking about entropy impairment in this case, what we are talking about is minimizing the amount of branch weight. We have a conserved branch weight, so we're trying to minimize the amount of branch weight whose entropy is impaired by matter. And it turns out the way to do that is to, well, first of all, it would be nice to get all the matter sort of clustered together in a small region and then have that moving very quickly in the codimension so that it experiences a lot of time dilation, and that time dilation reduces the 4-dimensional volume associated with that matter and therefore reduces entropy impairment. But at the limit, what happens is we put all that matter, it would be nice to put all that matter on a branch of minimum branch weight, and in that way minimize the amount of branch weight that is exposed to the entropy impairment of this matter. And that minimum branch weight is a branch weight of 1. It turns out that you cannot actually, because of our Ricci flat constraint on this metric and the topology of these defects that we can make, you can't actually tie a knot. You can't have one of these knots on a branch of weight 1. The geometry of this knot does not allow that. So instead, what we do is we get them onto a branch of the smallest possible weight that works, and this configuration that packs the most knots into the least amount of branch weight used. To do that, what we do is we create a region sort of at the middle of this distribution of matter that has a branch weight of 1. And then at the boundary of that region is all the matter, all the knots that have ever fallen into this black hole. And so it goes a flat region of spacetime with branch weight 1, then a thin shell of one knot thick shell of all the matter that's ever fallen into this black hole. And then on the outside is sort of the normal Schwarzschild geometry. And so we can think of that as being the event horizon effectively is the location of this thin shell of knots. And then we can look at the corresponding animation in this picture, and we see that we have this flat region of spacetime, branch weight 1, all the knots that have ever fallen into this black hole at the event horizon, and on the outside we have these standing waves that correspond to sort of the normal Ricci flat Schwarzschild geometry. There's no singularities in this picture, and the information paradoxes associated with entropy of a black hole, I think, are greatly reduced because in some ways we can say that the shell of matter at the horizon is a record of all the matter that has fallen in. The next force that we'd like to take on here is electromagnetism. We remember that we needed this metric h mu nu to keep track of the branch weight. We wanted branch weight so that we could do a well-behaved branch manifold. So the branching stays finite. So we needed h mu. We needed h mu to see curvature. We used h mu nu to make the branch weight by using the volume element of h. But this metric h has more information in it than just its determinant. And we want to know, does that information in h affect the entropy of spacetime? And the answer is yes. And we're not going to go into all the details on this, but it turns out that one of the ways that h mu nu has information is that h mu nu is not identical to the metric of the 5+ one-dimensional space. It is a different way of measuring distance. And briefly put, and this is not enough information to really understand what's happening, but just a hint that there is some sort of meaningful structure here. Briefly put, h mu nu has its own forward cone. So points that are at positive, if I pick some point P, there's some set of points that are at positive time-like distance from P, and H has a forward cone that corresponds to those points, and the metric of the larger space has a set of points that are in its own forward cone, in the forward cone of its own metric, and the forward cones of H and the embedding space metric may not perfectly match up. And the extent to which they do not match up is the extent to which this metric H affects the entropy of spacetime. And again, this is where we're going to kind of leave that story aside, but it turns out that it has an effect on the entropy. And so we can ask, well, how do we quantify that effect on the entropy? To do that, we use this antisymmetric tensor. From h mu nu, we get an antisymmetric tensor f mu nu. And the amount by which the entropy is affected on spacetime is in proportion to the tensor contraction f mu nu, f mu nu. And this is relevant, this is interesting, because electromagnetism is described using an antisymmetric tensor, and the Lagrangian of electromagnetism is f mu nu, f mu nu. And so those features of this entropy impairment match with match between the description of knot physics, where it comes from this metric h mu nu, and it matches with the description of the standard model, where we have electromagnetism described with this tensor in that particular Lagrangian. Well, it turns out that these knots are a good fit for charge sources of this field. And the reason is that these knots we remember they have this particular homeomorphism class. These knots allow the field F mu nu to run up to a finite maximum value. So if I have a point source, the field gets stronger and stronger as you get closer to the point. And if you have a point source for an electromagnetic field, the field runs up to an infinite value. The field becomes infinite at the point, and the field energy at that point is also infinite. However, these knots allow the field to run up to a finite value because these knots have non-trivial topology. Field runs up to a finite maximum, and that finite maximum value has a finite total energy. We're gonna there is a way of unifying electromagnetism with the weak force called the electroweak unification. And here it's a geometric picture. If we look far away from a knot, spacetime is flat. But at a knot, spacetime is not flat, and this knot bulges up out of the spacetime manifold. And so if you imagine that this knot is in motion with a velocity v, and we pick some point on this knot, there's a tangent space to the point on the knot. And v may not be in that tangent space. V might be sort of pointing out of the spacetime manifold at that point. Well, if we ask how does this, what is the kinetic energy? How does the energy transform as a result of this motion? We would calculate that kinetic energy, that energy associated with motion, using a Lorentz boost. And if we pick some point on this knot where there is some stress energy tensor, some energy associated with fields at a point on that knot, and then we Lorentz boost using a velocity vector that is not in the tangent space, the result is that energy is going to Lorentz transform with rest mass. And so if there's a field on this knot, that field has energy. And effectively, at any point where this knot is not parallel to flat spacetime, where the geometry of the knot is not parallel to flat spacetime, that field has rest mass. And this is starting to look like the electroweak unification, where the electromagnetic field or the electroweak field has mass. For example, here we show a field oscillation where the field is sort of rocking back and forth on top of a knot. So this knot has geometry that bulges up out of flat spacetime. The field rocks back and forth. It's an oscillation of the field. It's an oscillation that leaves the charge unchanged, but this oscillation occurs in a region of spacetime where the geometry is not flat and therefore has mass. And this is the Z boson. It has mass, does not transfer charge. This is the Z boson of this theory. On the other hand, we could look at an example where we have, for example, a muon that decays to make a mu neutrino, an electron, and an electron antineutrino. And in this case, the field sort of moves down the side of the knot. And by moving down the side of the knot, it's moving over a region of spacetime where spacetime is not flat, which means that the field has mass. It is a motion of the field where the field has mass, and it does transfer charge. And so this is the W boson of this theory. And if we want to describe all of this using some sort of coordinate system, well, a four-dimensional coordinate system isn't quite going to do it because we need to keep track of where space-time is not parallel to a flat space, and that's not going to work with 4 dimensions. On the other hand, if we use a 6-dimensional coordinate system, then we have a lot of redundant information for describing a 4-dimensional manifold. And so here again, we see where information is a big part of the story. We fix the redundancy. We have extra information in that 6-dimensional coordinate system. We can fix the redundant information using gauge groups. And so if we're far away from one of these knots, then we can pick some point on space-time that is flat, and we have 2 extra dimensions. If we were to rotate in those 2 extra dimensions, it would have no effect on physics or entropy, and therefore no effect on the action. And so we can freely rotate in those dimensions without having any effect. But rotation in 2 dimensions would be done using a gauge group SO2. It turns out that SO2 is isomorphic to the gauge group U of 1. There are 3 dimensions that are parallel to flat spacetime. Spacetime manifold is the manifold with 3 spatial dimensions, and so there's 3 dimensions that are parallel to flat spacetime. And any of those dimensions, any of those directions, can be perpendicular to the tangent space on the knot. So we can pick some point on this knot where any one of those 3 dimensions is perpendicular to its tangent space, which means that the direction should have no effect on the action, the entropy, the behavior, the dynamics at that point. With 3 dimensions, we can rotate those 3 dimensions using a gauge group SO3, except that this fermion topology is non-orientable. We have this particular homomorphism class that is these knots, and it is a twist. It's non-orientable. And so if I have some 3-dimensional coordinate frame that is parallel to the spacetime manifold, and if I have some, we'll say, right-handed frame that I then translate across flat spacetime through this knot and out the other side, my right-handed frame will have turned into a left-handed frame. And that is not something that is possible with the gauge group SO3. Instead of SO3, we need to use the double cover of SO3. And that does allow for that kind of transformation. The double cover SO3 is SU2. And so combining these 2 things, SU2 and U of 1, I get a description of a combined description of the field on the knot and far from the knot. And that combined description is uses a gauge group SU2 cross U1. And that gauge group is kind of it is the gauge group of the electroweak unification, and it's kind of a signature for the electroweak unification. Moving on to the last of our forces, the strong force. We have these topological defects of this particular homeomorphism class. And it turns out that these defects can link to each other. They link to each other in the sense that they cannot be separated. If we link them, if we link these knots, then those linked knots are the quarks of this theory. For example, a proton consists of 3 linked knots. And the linking is not quite the same as linking circles, but for the purpose of our animation, it is close enough that we can use a lot of the properties of linked circles to understand the behavior of these linked knots. For example, if these knots are close to each other, they don't exert any force on each other. As long as they stay close, they don't exert any force. And using the terminology of quarks, that property that they don't exert any force on each other in this regime is asymptotic freedom. So that would be the asymptotic freedom of these quarks. But because they're linked to each other, they cannot be separated. And that property that quarks cannot be separated is called quark confinement. If we do try and separate from each other, these quarks from each other, then they do exert force. And that exchange of force between these quarks is the gluon of this theory. And now we can ask, well, if our dynamics are coming from entropy maximization, how can we understand the effect of this linking on the entropy? And so to do that, we want to get a bit more quantitative, and we say that each of these quarks, we'll label them A, B, and C. Each quark is displaced from the center of the particle by some displacement vector. So quark A has vector A, B, and C respectively. We remember that we're in a larger space that has 5 spatial dimensions. And so the displacement from the center can be encoded using a 5-dimensional vector. So each of these quarks is displaced from the center of the particle with vectors A, B, and C, A1 to A5, B1 to B5, and C1 to C5, respectively. If we also say that the center of the particle is the origin of coordinates, then these vectors sum to 0. So A plus B plus C equals 0. We know just from the topology, these quarks cannot be separated from the particle. If I were to try and pull one of these quarks away from the others, there's a limit to how big I can make vector A before it is colliding. It is the linking effect is preventing it from moving any further away. And so to say that there's a limit to how far these quarks can be separated from the center, we say that there's a limit to the magnitude of these displacement vectors. And so vectors A, B, and C all have magnitude less than or equal to 1 in some units. Exactly how far do they go from the center? We're going to neglect that in terms of meters or whatever it is. We'll just say in some units, the magnitude of these vectors must be less than or equal to 1. But a 5 vector with magnitude less than or equal to 1 is equivalent to saying that I can add some 6th non-physical coordinate such that each vector has a magnitude equal to 1. So now I've got a vector, instead of A1 to A5, I have A1 to A6, where A6 is the quantity that is necessary to make the magnitude of this vector equal to 1. So I had a 5 vector with magnitude less or equal to 1. That constraint is a little harder to work with than a vector's magnitude is equal to 1. And so I just add in a 6th coordinate that takes my 5 vector to a 6 vector, and that 6 vector has magnitude equal to 1. But a 6 vector with magnitude equal to 1 is equivalent to a complex 3 vector with magnitude equal to 1. So now instead of A1 to A6, I have A1 plus A2i, A3 plus A4i, A5 plus A6i. This complex 3 vector. I do the same thing to vectors B and C. And now each quark has a complex 3 vector, magnitude equal to 1 and summing to 0. And that is the description of the color charge in the strong force in quantum chromodynamics. Well, how do these color charges, how do these positions affect the entropy? How do they contribute to the action? Well, if these quarks are closer to each other than a knot radius, then their position has no effect on the entropy. And it is guaranteed, to say that their positions are described with these complex 3 vectors whose magnitude equal to 1 guarantees that their displacement is closer than the knot radius. So the values of these complex 3 vectors do not contribute to find a gauge group that describes this relationship. Well, the gauge group that applies to complex 3 vectors is SU3. And so altogether, we have a color charge for each quark and a gauge group SU3. And this is the description that corresponds to quantum chromodynamics. In this way, we use geometry to reproduce quantum chromodynamics from the standard model. So have this spacetime manifold with knots. It turns out that we can produce these topological defects, these knots that are the particles of this theory. The manifold is branched, which allows quantum properties. And the dynamics are under-constrained, which allows entropy, and entropy maximization produces familiar fields and forces. We've covered a lot of ground here, but there's quite a bit more. It's available at the website, notphysics.net. And if you're interested, I would invite you to check it out. Thank you.